Howdy, we're Team 6517, also known as SoKno Robo. Not SoKno Robo, it's SoKno, for South Knoxville, where we're based in. It's in the foothills of the Smoky Mountains, a relatively low-resource region, and while there's just 15 of us, we're all passionate for robotics. Let me introduce you to Chell, a robot for the 2020 Infinite Recharge game. She weighs 118 pounds and can reach speeds of 18 feet per second. In total, she's a culmination of at least 3,800 hours of work.
Our team's engineering and design process starts out in CAD, with one subteam taking a system each. We begin by creating 2D kinematics for each element of our subsystem to minimize any interference problems that can be fixed right away. After that, we CAD out the entire subsystem, and if other parts are available, we combine them together to see if there's an interaction problem that we did not notice before. Then we begin to prototype our design using laser-cut wood and 3D printed components. This phase will normally go through 4 to 5 iterations before a final design path is decided. In the end, we have our entire robot with all the subsystems fully functioning in CAD. Our robot is 100% fabricated in-house to speed up our prototyping process rather than going to partners for the machining. This is because we have multiple machining capabilities within our shop, including a CNC router, CNC laser cutter, and multiple 3D printers. All of our team members are also trained to generate their own CAM and machine their own parts for their sub-team.
We designed our launcher to be both accurate and precise, while also able to launch 5 power cells in less than a second. We needed this quick launching capability because we expected stiff defense in competition. We wanted to be able to launch within a small window of time for this reason. The shooter is composed of a turret with 340 degrees of rotation that stays locked onto the target with machine vision tracking. The launcher also has an infinitely adjustable hood that will adjust for any distance to the target. The launcher is powered by 2 Falcon 500s, meaning we don't have to worry about the power behind our shots and can shoot from anywhere on the field. We chose to automate the launching process with continuous auto tracking in order to take load off the driver and to quickly provide a launching solution at any moment. We first prototyped the launcher out of wood and 3D printed parts to test 6 different iterations of the design. Turret tracking, launcher power, hood angle, and the launcher feeding process were all tested in this phase. The final turret and launcher design uses machine vision tracking for the turret, and the hood angle and motor speeds automatically adjust based on distance of the target. Here is the final version in action. You will be able to observe that the turret is tracking the target and the hood is automatically adjusting based on distance.
We designed our autonomous routine to pick up and shoot 8 power cells within 15 seconds. We generate paths using PathWeaver. To track the position of the robot, we use a ramset controller, and for the robot's orientation, we use the encoder positions in the gyroscope. We then use machine vision to track the target and to determine range for shooting.
This indexer stores the power cells and feeds them into our launcher mechanism that then goes into our shooter. It can hold the maximum 5 power cells and ejects them all in less than 1 second. We have also incorporated many different mechanisms to make our indexer unable to jam, the main mechanism being 3 independent motors. The videos on the left demonstrate the iterative design process that we went through with the indexer. The first video was an early prototype with an issue of the balls jumping out of the top. Due to this, in the second video, we included a top to cage in the balls. After that, we had the bottom video that includes a top agitator wheel that will help properly feed the balls. Lastly, the main video showcases our final polished design. Overall, the path to creating this indexer was iterative. In the end, we had about 15 different design changes. However, this enables us to have an indexer that cannot jam while holding 5 balls that can be ejected in less than 1 second. This design also required immense fine-tuning of each independent wheel to ensure that all the balls would be fed through properly. We also had to include a layer of Teflon on the inside of the indexer to help ease the power cell's path through the tight space.
We designed the climber to be able to climb at any orientation of the shield generator. The climber takes less than 6 seconds to launch and complete a climb. The climber uses a collapsible design that keeps all parts of the climber under the maximum height to travel under the trench, while able to extend to 84 inches at its maximum. The climber uses a Falcon 500 to power the lift, and uses a ratchet and latch mechanism to hold the robot to ensure we will never fall. On the left, the robot is shown activating the climber, where pneumatics lift the climber and the latch is released, launching the climber out with constant force springs. To the right, the climber is shown retracting under full robot weight and relatching when fully retracted. The hook that is on the climber rotates to match the shield generator angle, keeping the robot weight perpendicular to the ground and allowing it to keep most contact possible and minimize torque on the robot. If a match finishes before a full climb or the latching system fails, the ratchet acts as a safety measure, keeping the robot from falling.
Our intake is a rather simplistic design that has a rather intricate background. It intakes 3 balls at once without losing the balls. The material of the arms is HDPE plastic, allowing them to be flexible, yet impact resistant if our intake gets hit during the match. We are also able to retract our intake when it is not in use during the match. However, the intricacy behind this design lays with the interfacing that the mechanism has to complete. This system nests between 2 other systems with less than 6 inches of space, which limited the available design options.